Do 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 do. Now we're doing work by non-conservative forces. So everything we've done thus far with our conservation of energy has been with conservative forces. We haven't lost our energy. What we're going to do now is use non-conservative forces. We're going to use forces like friction, where you lose your speed due to friction, and that energy is just kind of lost as heat. You know, if you rub your hands together very quickly, you'll warm them up, but then that energy's just dissipated away. It's still, in the room itself because you're like heating up the gas particles, but in terms of it being in your hands, it's gone, and you're not getting that energy back. So these non-conservative forces cause systems where within the system itself, we're losing our energy. It's going outside the system, and we have no way to get it back. So what we can think about here is when we do work on an object, which we've talked about at the very beginning of this unit, work equals a force dotted with a displacement. We can think of the work done on an object as being equal to its change in mechanical energy. Remember, change is a delta. So if we wanted to, we could write this as a final minus an initial, because a delta will always be final minus initial. Now, because of this, we can actually expand the work energy theorem just a little bit further. The work energy theorem, which was originally that work equaled a change of kinetic energy, we can consider that work energy theorem can be written as a conservation of work energy completely. Now, there's a few different ways to write this. I'll write them all out. Whichever one you like to use, I'll show you which one I like personally, but whichever one you like to use, feel free to use it. But we'll put everything out right here. First, if we expand this equation up top, we can say that the work will equal, well, these energies, EF and EI, that's a combination of kinetic and potential. So this is going to be like kinetic final plus potential final minus kinetic initial minus potential initial. And we subtract both initial for kinetic and potential because that negative is on both the initial energies. So that's one way you could write this equation out. There's nothing wrong with it. My personal favorite way to write the equation is to take that initial kinetic and the initial potential and move them over to the other side so that they are with the work. We could write that then as the final kinetic plus the final potential equals the work plus the initial kinetic plus the initial potential. And remember, in both of these cases, that initial potential includes both gravity and springs. So your potentials for final and initial could be more than one thing there. Okay? If you wanted to, this here is my favorite, but if you wanted to, you could recall that work is that force dotted with a displacement. So you could write this as a kinetic final plus a potential final equals Fx cosine of theta plus kinetic initial plus potential initial, with potentials being possibly both springs and gravity. All of these equations are the exact same. We will often be transferring this work into our Fx cosine theta. But if you forget that work is Fx cosine theta, then maybe the equation here in pink is a little bit easier for you to remember. Or at least write it down all in one go. Okay? Now, the reason why this equation kind of looks like it does is if we think about it, if you have an object moving on flat ground initially. Let's say you push a box with some initial speed, but then it goes over a rough section of carpet with friction and slows down to a stop. And this is all done on a horizontal surface. Well, if it was done on a horizontal surface, our potentials wouldn't change, so we could ignore them, and there's no spring. What this is saying here is that if we stop, the final is going to be 0 for kinetic energy. And we had some positive number here initially. This means here that the fx cosine theta, because it's friction, if that box was acting to the right, or moving to the right with some velocity, its delta x was to the right, the force would have been acting to the left then. That's our force of friction. We know friction is fun, mu n or mu mg. And that means the angle between these is 180. Cosine of 180 is -1, so this fx cosine theta would be a negative number. And a negative number plus a positive number can give us 0, because that's all we have left on our final side of things. So that's what we're trying to map here. We're saying, look, if we have some initial kinetic energy, but then all the friction uses that energy up, takes it away, we're left with nothing, assuming that box stops. So that's the idea we're going to be using here for our type of problems. We're going to be doing one example here, and then one practice problem in our next video. But let's take a look at an example of this, kind of how it looks here for our example problem here, okay? In our example, we have a kid, and just a few weeks ago, we had a ton of snow in our region. A total, like, winter blizzard, right? The kid and the sled have a combined mass of 66 kilograms. So here's our mass. And they're moving at 12.5 meters per second at the bottom of a 3.75 meter high hill. The sled slides up the snowy, frictionless hill, but then it slides along a dry top. So maybe it's like a road up there, which does have some friction with a coefficient of 0.5. We need to calculate a whole bunch of stuff here, but let's start the same classic way Grandpappy Botzer always said, by drawing ourselves a picture. In our picture, we have some snow at the bottom and a snowy hill. And it doesn't matter how steep our hill is, it doesn't matter if our hill has any bumps in it. The hill is frictionless, so the hill itself is conservative. It's a conservative force there. But once we get to the top of the hill, we hit that kind of road, and we have some friction here. Okay? So we know that the coefficient of friction, mu, is 0.5 at the top of that hill. We also know a few other things. From the bottom of the hill to the top of the hill, this is a height of 3.75 meters. We also know that initially, when the child was riding their sled, I can't draw a sled. That's good enough. That's a kid. When the kid was initially on the bottom of the hill on the sled, he was moving, or she was moving, at 12.5 meters per second, and we knew the mass was 66 kilograms. In this problem, due to the friction at the top, due to that like parking lot or whatever, this child is going to stop at some point. They're going to get to the top here, and their final velocity is going to be 0. I wrote v prime for final, but you could write vf if you wanted to. And this implies that at the top, their kinetic energy will be 0. But it also implies that they have traveled some distance, delta x, through the top here. And that they stopped due to the force from friction. So let's try to set up a kinetic energy equation here and see where we'll have to go from that. It doesn't matter if you put your finals first or the initials on the left-hand side. As long as it's the initials plus the work equals final, you'll have the same thing. So let's see what we had initially. Initially, we have an initial kinetic energy because we're moving at some speed. And we know in this problem there's a change in height for a gravitational potential energy shift. But let's make a reference position. Let's make our reference position either the bottom or the top. Let's just make it the bottom. Making it the bottom or the top makes one of those values for the beginning or the end 0. Let's just make it the bottom for now. So if our bottom is the reference position, then we're not going to have any potential energy there. So if we set this up, we are going to have initially some kinetic energy. We're going to have a 1/2 mv squared, so 1/2 times the mass of the child, 66, times their speed, 12.5, squared. The gravitational potential energy in the beginning, because we're at our reference point, is 0, so we don't have to put anything there. And then let's just, for right now, let's just put in plus some amount of work that is done. Okay? This will have to be equal, on the other side, to all of the final pieces. The final pieces being the gravitational potential energy that we've gained, the mgh, so that's 66 m times g, 9.8, times the height of 3.75. And then our kinetic energy at the end is 0. Now, the work that was done by friction up here, that is this work down below, okay? That was the work that is going to be stopping our sled. And in doing this, we've actually set up our entire problem. And we can actually solve for part A and for part B here. Part A is just asking, what is the initial kinetic energy of the sled and the kid? That's the 1/2 mv squared. So if we throw all these into the calculator, the 1/2, 66, the 12.5 squared, we're going to get a value, and be careful with your squaring. That square only happens on the 12.5. We get a value of 5,156.25. That's the initial kinetic energy. That gets added to some work. And then this equals, in part B, the final potential energy of the sled and the kid. In this case, that's the 66 times 9.8 times 3.75, which gives us 2,425.5. So that's part A and B right there. We found the initial kinetic energy. We found the final potential energy based off of our reference position. Now, let's take a look at this equation right here that we have set up. This equation's a little weird because 5,000, or a little bit more than that, plus W equals 2,425. This means that this W here, this W better be a negative number. Because if it was a positive number, 5,156 plus any positive number is not going to get us a smaller value. This work has to be negative. It has to be a negative quantity. We can figure out what this work value actually is. If we simply solve for work here, we'll subtract 5,156.25 from each side. We'll find out what our work value is. So 5,156.25, or excuse me, 2,425.5 minus 5,156.25, we find here that our work is equal to negative 2,730.75. And that unit is still joules. And when we think about this, this is the work done by that friction surface to slow our sled down. Let's draw that sled moving across that ground again. Here's the top of the hill. There's like the asphalt. If our sled is moving across the ground, it's moving some displacement to the right. But the friction is acting to the left. The angle between these is 180 degrees, which means that this force dotted with the displacement, this work, is going to be negative. If we substitute our equation for work in here, Fx cosine theta, what we'll have is friction times our displacement times the cosine of 180 degrees. This will equal negative 2,730.75. This goes back to what we did at the beginning of our unit. If you recall in the beginning of the unit, we know that the cosine of 180 is equal to negative 1. By definition on the unit circle, that is cosine of 180. So the cosine of 180, this negative 1, it gets rid of the negative on the other side, which was very, very nice for us. So at this point, it looks like our equation is just friction times displacement equals 2,730.75. But we don't know that force of friction off the bat. They don't just come out and say, here's the force of friction. What they give us is the mass of the child and the coefficient of friction of the top of the hill. What we need to remember is we know an equation for friction. We know that friction is fun. It's mu times the normal, which on flat ground can be written as mu mg, because that normal is equal to the weight of the object. That's what we saw a lot back in Unit 6. We're starting to pull a bunch of units together for this complicated physics. So we can plug umg, or mu mg, in for F, and we get the equation mu mg x equals 2730.75. And now we can finally throw in a bunch of numbers. Doing this, we know that mu is 0.5. We know the mass is 66 kilograms again. We know gravity is the classic 9.8. X is actually what we're looking for in part B. It's how far did that child slide before they came to a stop. And that's going to equal 2730.75. At this point, it doesn't matter how you like to do this algebra. If you want to combine all of these terms together and then divide, you can do that. If you want to divide by each term individually, you could do that as well. It's the same thing. I'm going to write it so that I divide by each one individually, so I could just write this as x equals 2730.75, that's a 3, divided by 0.5, 66, and 9.8. Be careful on the calculator if you're typing in like this, because while it looks like these are all multiplied, if you accidentally just multiply with these on the calculator without doing parentheses properly, you might accidentally bring them into the numerator. So I highly suggest that right now you grab your calculator and you try to work this out and get an answer. If you want to just multiply that denominator first together to get that number and then do the division, that's fine. If you want to try to do it in one step, that's fine too, but let's make sure that we're on the same page and get the same answer. When I do this, let's see what I get. I get 8.44 meters. And hopefully you do too. If you didn't get that, try multiplying everything in the denominator together first. You should get 323.4. And then do that division. Sometimes people feel that that's a little bit easier to do than trying to divide by everything over and over and over again. Okay? But that's how we include a non-conservative force like friction in our conservation of energy problems. Okay? We still set up our same equation with one extra piece here, this work, which we know is Fx cosine theta. And then as we bring that through in these problems, we're just working out the algebra to get down to our final answer. And we are making sure that when we have friction, that cosine of 180 is brought into effect because there's a -1 term there, which we saw got rid of a negative. That's very important for this. A lot of people mess that up. If you mess that up, you might accidentally add things when you should be subtracting them, or things might go in a weird way, and you might get funky answers, okay? But that's how we set this up. In our next video, we'll look at another practice problem for this. But for right now, this problem is finished. And until next time, adios, and take it easy.